Alright guys, well I knew you would be missing me if I didn't give you a little bit more material today, so I'm going to do this with a video. I hope you don't mind watching this. Of course you can watch this later, and you can also rewind, pause, and so on and so forth as you go through this in the future. You can watch it at home or whatever, but you can also ask me questions. I'll be back soon to answer questions about this section. So I'm going to talk about section 8.3. It's called Annihilators. All right, so we've been killing things by calculating kernels of transformations. Now we're going to annihilate things. This is section 8.3. Here's the basic idea. We've just learned in the last class or so how to solve the homogeneous linear nth order differential equation L of y equals 0. That's what we did in the last section. We write down the auxiliary equation, we find the roots, and we deal with repeat or complex roots as appropriate. Okay? But what if we now want to go back and solve a non-homogeneous differential equation of this form? So the right-hand side has some function, which is usually written as capital F. And what if we wanted to solve a non-homogeneous equation like that? Turns out there are a couple of different methods that we're going to learn about that you can do to do that. Both of them have the same sort of structure to them. So I'm going to outline the structure of this, but today we're only going to talk about the first of the two methods, which is the annihilator method. Okay? But there are three steps that I'd like you to be thinking about. The first one, the very first thing you're going to do in order to solve the non-homogeneous differential equation is you're going to first solve the corresponding homogeneous differential equation. Well, that's what we've already learned how to do. Okay? So we're going to solve the corresponding homogeneous differential equation L of y equals 0. Okay, so the original homogeneous differential equation. And the solution that we get to that, we've been writing that as y of x in class. I'm now going to call it y sub c of x. Okay, and this is called the complementary function. So there's going to be two parts to our solution, and we're going to highlight both of them. So the first part here is called the complementary function. Complementary function. Okay? So that's called y sub c of x. All right? The second step in the process is going to be to find somehow, and I'm going to explain how, find one particular solution. I'm going to call it y sub p of x. So one particular solution to the differential equation L of y equals f. Okay? So you don't have to find all of the solutions to this non-homogeneous linear differential equation. You just have to find one solution to it. One specific solution. Okay? That's the particular solution, y sub p of x. Okay? So what you do, the final step then, is to get the general solution to this non-homogeneous differential equation, you're simply going to add together the complementary function to the particular solution. So you're just going to write down your, what I'll call the final answer here. And the final answer is simply y of x equals y sub c of x plus y sub p of x. Okay? So you simply add the two parts together. Okay? So I hope that that makes sense. Step one, of course, we already learned how to do in the last section. Step two is the part that's new in this section, in what I'm going to talk about in this video. And then step three is just wrapping it all together, adding the two solutions from the two parts that you have. Okay? So there are two methods for finding one particular solution to L of y equals f. And the reason we have two methods is that neither one of those two methods that I'm going to explain works in all situations. Okay, so we need to have multiple ways of approaching these problems. So the annihilator method is one method. I'm going to talk about that in the video, and then when I get back to class again, next week we will talk about what's called variation of parameters. Okay? So let's talk about step 2. How do we get one particular solution to the differential equation? Well, here's the idea. We already know how to get the solutions if there's a 0 on the right-hand side. Okay? So what I'm going to hope to do here is I am going to hope to find a way to annihilate capital F. I'm going to try to annihilate capital F. I'm going to try to make it become 0 through applying operators to it. Those operators are derivative operators. Okay, so I can annihilate functions by taking derivatives sometimes. For example, you all know that if you have, say, a constant, you can annihilate it by taking the derivative of a constant, because the derivative of a constant is just 0. Okay? So we're going to talk a little bit about how to annihilate functions that might appear on the right-hand side of this non-homogeneous differential equation. If we can find annihilators for that right-hand side, we can turn it into a 0, right? And then we'll be able to go back and use what we already learned about how to solve differential equations that have a 0 on the right-hand side. Okay? That's the idea. Okay? So let's see if we can do this. So to do step 2, in my outline that I just presented a few minutes ago, we're going to try to find an operator. I usually write A of D for this, an operator such that A of D, when you apply it to capital F, gives you 0. Okay? So here's an example. Okay? If capital F is equal to, let's say the right-hand side is x squared, right? Then you can think for a minute, what would annihilate x squared? What combination of derivatives? The D is the derivative operator, yeah? So what derivative operation could we use to annihilate capital F? Well, the answer is, I'm sure you probably can think about this for yourself, if you differentiate x squared 3 times, right? Derivative, 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 it'll eventually become 0, right? You take x squared, take the first derivative, it becomes 2x, take the second derivative, it becomes 2, and take the third derivative, it becomes 0. Okay? In fact, you probably could figure out more generally that if capital F is equal to, let's say, a sub k x to the k plus a k minus 1 x to the k minus 1 plus dot 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 plus all the way down to a naught. If I have any polynomial on the right-hand side, any polynomial at all, then the annihilator of that would just be to take one more derivative than the degree of that polynomial. Okay? So annihilating polynomials isn't too bad. All right? Just look at the degree of that polynomial and jack that power up by 1. Okay, let's take another example. What about if capital F is equal to the sine of x? Okay, so take something like the sine of x. Well, in order to annihilate that, the annihilator of sine of x, the way that you can do that is, if you think about it, if you take 2 derivatives of the sine of x, okay, if you take 2 derivatives of it, you'll get negative sine of x. And if you then add that back to the sine of x again, it becomes 0, right? Okay, so this annihilator would work for the sine of x. You can just check that. If I take d squared plus 1 of sine of x, you will get 0. Okay? And actually, the same annihilator would work for cosine of x. So I'm just going to add that here as well. So if you have sine or cosine of x, you can annihilate it with d squared plus 1. Okay? More generally, if you have, let's say, sine of bx or cosine of bx. When you take derivatives of sine of bx or cosine of bx, you're going to be pulling b's out in front every time you take a derivative. So we do need to modify our annihilator just a little bit. Okay, if we take two derivatives of, let's say, sine of bx, we'll get negative b squared sine of bx. Yeah? So I can actually annihilate it with b squared plus b squared. Okay? So again, if you apply this to the sine of bx, so if I come over here and put sine of bx right here, you take two derivatives of this and then add b squared times this, you will in fact get 0. Okay? So those are the annihilators for the sine and cosine of a multiple of x. I should also make a point that if you put constants in front of these expressions, so if I have, you know, if f is equal to k times the sine of bx, it doesn't change the annihilator at all. Okay, because that k, if I put k times the sine of bx here, you're just going to be able to factor the k right out of everything, and you'll just get k times 0 when you evaluate that. So constants in front of expressions don't matter at all. Okay, let's do another one. Hopefully you're getting the hang of it. We're looking for annihilators. That is combinations of derivatives that kill the function that we're looking at. Here's another one that's very important. Suppose that my function f is e to the ax. All right? And I want to annihilate it using derivatives. I want to use derivatives in such a way that it becomes 0. Well, if I take a derivative of e to the ax, I'm just going to get a times e to the ax. Right? So the derivative of e to the ax is a times e to the ax. So if I make this annihilator expression, d minus little a, that is going to annihilate e to the ax. Check it out. If I multiply this by e to the ax, the derivative of e to the ax minus a e to the ax is in fact going to be 0. Okay? So that is the annihilator of e to the ax. Okay? Now, of course, there's lots of other expressions that you could have for capital F as well. Right? So I've talked so far about polynomials, about sine and cosine, and about e to the ax. I'm going to give you a table of annihilators. You're not going to have to memorize what annihilator you need to use for what function, because I'm going to give you that table that shows you what those annihilators are. Okay? And so you can handle even expressions that are combinations of the things that we just talked about. You can take things like, you know, a polynomial expression with an exponential expression with a sine or cosine expression and multiply it all together, and there is an annihilator for that as well. And it's in the table of annihilators that I'm referring to. Okay? The other thing I wanted to mention is that if you have a sum of two functions, so one last thing here, and then we're going to see how this can be used to do step 2. All right? If you have capital F is equal to, let's say there's two different functions here on the right-hand side, right? And let's say that A1 of D annihilates F1, and A2 of D annihilates F2. Okay? Then the annihilator of F1 plus F2. Okay? If I have, let's say I have, you know, this is an example, let's say I have e to the 5x plus cosine of 3x, right? And I want to annihilate that. So, if this is capital F, then what's the annihilator? Well, the formula, as it turns out, what you need to do here is you need to actually multiply the annihilators. So you don't add the annihilators, you actually have to multiply those annihilators in order to annihilate a sum. So for example, up here, the annihilator of e to the 5x would be d minus 5, and the annihilator of the cosine of 3x would be d squared plus 9. So this would be your annihilator for this function, capital F. Okay? Anyway, there's a whole table of annihilators that you can use, and it will work for a lot of functions, capital F, that you might have. Now, how do you then go from that to actually doing step 2? How do you actually now find one particular solution to this non-homogeneous differential equation? Okay? I think the easiest way to show you is to just do an example. Okay? I'm going to do an example here. Let's try to solve the following problem. Y double prime minus y equals 16e to the 3x. Okay? Let's go through the 3 steps. Step 1 is where we first solve the corresponding homogeneous differential equation. Okay? Now, the auxiliary equation for this is very easy. It's just r squared minus 1 equals 0. So I get 2 distinct roots, plus and minus 1, to that auxiliary equation. And so I can write down my complementary function very easily. c1 e to the x plus c2 e to the negative x. I'm going to put a box around that because we're going to need that later. Okay? So we have 2 real distinct roots. Yeah, there's no repeats, there's no complex numbers. So we're just going to put this down like that. Okay. Now let's talk about step 2. This is where the new material is coming into play. Okay? For step 2, here's my problem right here. I need to figure out an annihilator for e to the 3x. Remember that the 16 in front doesn't matter. Okay? You don't have to worry about constants that are out in front. Well, I happen to know that the annihilator of e to the 3x is just d minus 3. d minus 3. Okay. What I'm going to do is I'm going to apply that annihilator to both sides of my differential equation. Okay? Notice that my differential equation that I was given, if I write it in operator form, it looks like this. This is the operator, using the D notation in other words, this is the operator version of the problem I was given. I am going to slap a d minus 3 in front of both sides. In other words, I'm going to apply this operator d minus 3 to both sides of that differential equation. Of course, on the right side, I'm going to end up getting 0, right? On the right-hand side, I'm going to be getting 0 because I have chosen an annihilator for that right-hand side. On the left-hand side, of course, I just have now made for myself a slightly higher degree differential equation. So I'm going to come back up here now and give myself a little more room on the top. This is homogeneous now, right? I can treat it the same way that we would have treated the problems in section 8.2, right? If we think about it, the roots of the auxiliary equation of this differential equation are going to be plus or minus 1 and 3. Okay? Notice that the old roots, plus and minus 1 that we had found in step 1, are always going to be present again in step 2. That's because you haven't lost this d squared minus 1 here. You haven't lost what was on the left side of that differential equation. So those roots, those are the old roots that we already had found in step 1. The new root is the one that's right here. And what you want to do is you want to say to yourself, well, okay, so to write down the solution to this, right, to write down the solution to this differential equation, you would write down c1 e to the x plus c2 e to the negative x. I'm going to stop for a second. This is just the complementary function. We've already noted that before. But I'm now going to be adding on, remember how this works, the final answer, this is really kind of step 3. the final answer is just the complementary function plus the particular solution. Now, the particular solution, guys, okay? The next term that you would write down, I'm sure you're thinking of it, it would be C3e to the 3x. Okay? However, I am not going to write C3 there. I am going to use a different type of letter. The reason is that the constants that show up when you write down the particular solution actually can be solved for. We can actually find this number, capital A. Whereas C1 and C2, those are the general parameters that you're going to see in the general solution to the differential equation. The only way that I could solve for C1 and C2 is if I had been given initial conditions to go along with this differential equation. Here I didn't have any initial conditions, so I'm just going to write down the general solution to this differential equation. It means that you're going to have C1 and C2 in your answer. However, the particular solution is supposed to be specific. It's supposed to be particular. So you can actually figure out what that capital A is. Okay, and here's what you do to do that. Okay, to find what that constant A is, you simply substitute the particular solution into the differential equation. So we're going to plug y sub p of x into the dE, into the original dE. Okay, so I'm going to take two derivatives of that. So we're going to have a e to the 3x double prime, right, minus a e to the 3x equals 16 e to the 3x. All right. If we take two derivatives here, we're going to get 9 a e to the 3x minus 8 e to the 3x, a e to the 3x equals 16 e to the 3x. And you can pretty quickly now figure out that a is equal to 2. That's because you have 8 a's on the left side. The e to the 3x's can actually be canceled. And you just get 8a equals 16. And that means that a is equal to 2. So your particular solution, it really is very specific. It's 2e to the 3x. Okay? So now your final answer then, what you would write down and circle as the final answer on this problem would be y of x equals c1 e to the x plus c2 e to the negative x plus 2 e to the 3x. Here's the final answer. Okay? So most of it, this first part of it is just the complementary function. That's the old material. The new material is just telling you that you're going to be adding on a particular solution, and that's going to come from the new roots of the auxiliary equation that arise from the process of figuring out the annihilator. All right? And then you can actually solve for that constant there. Okay? Let's do another example, okay? Let's try another example here. So here's an example. Let's solve. Let me get the equation here. Y double prime minus y prime minus 2y equals 10 times the sine of x. Let's try this particular problem here. Okay? Let me get everything else out of the way. You can always go back and rewind later if you need a little bit of extra help with this. So let's take this problem. All right? First step is to find the complementary function, and so I just need the auxiliary equation here, which is very easy. Right? It factors pretty quickly. It's just a quadratic. So we're going to get the roots 2 and negative 1. Okay? So the complementary function then is c1 e to the 2x plus c2 e to the negative x. Okay, so let's keep this close at hand because we're going to need it later. Okay? Now let's go on to step 2. In step 2, we have to figure out an annihilator for the right-hand side. Well, that's going to be in your table, and we talked about it earlier. The annihilator, in this case, is d squared plus 1. Okay? If I apply that annihilator to the original differential equation, I will make the right-hand side 0. Okay? Now, on the left-hand side, I'm going to keep all of these old roots. These are the old roots here. But I'm going to generate new roots that really come from the roots of this annihilator expression, right? So you can start to realize that you can sort of short-circuit the process. I went through it in full detail on the first example, but I already know that the new roots are always coming from this, right? So those are going to be plus and minus I in this case. Those are the new roots. And those new roots correspond to the particular solution. See, I don't have to go back and write down the complementary function again, right? I can save this for later, okay? The particular solution really just comes now from solving, you know, writing down the expression that coincides with the solution that has those two roots. And the answer to that would be, well, this is just going to be sines and cosines, if you remember. So this is 0 plus or minus I. So you're going to get solutions, you know, e to the 0x times cosine of 1x. And the second solution is just e to the 0x times the sine of 1 times x, right? So we talked about that. That's back to section 8.2. Well, in other words, it's just a constant times the cosine of x plus another constant times the sine of x. This is what I like to call the form of the particular solution. This is the form of the particular solution. It's not the actual final expression because I haven't solved yet for a and b. Okay, to solve for a and b, I need to plug this particular solution into the differential equation. So, you know, I would have to take the derivative here, right? Negative a sine of x plus b cosine of x. I actually like to take all of the derivatives that I'm going to need first. So I need up to 2 derivatives of this. The second derivative is going to be negative a cosine of x minus b sine of x. Okay? So now I'm just going to plug this in to our differential equation. I have the second derivative, negative a cosine x minus b sine x. All right, and then minus y prime, that's negative a sine x plus b cosine x. And then minus 2 times y, so minus 2 times a cosine x plus b sine x. This takes a lot of room. Okay, and then that all has to equal 10 times the sine of x. The way to work with this expression now, guys, is to group all of the cosines together and all of the sines together. So if I look at it, I've got cosine of x, and here I have a negative a, here I have a negative b, and here I have a minus 2a. So that's the cosine part. And then I also have, right, I also have sine of x. I have negative b here. Here I have 2 negatives that makes a positive a, and I have a minus 2b over there, equals 10 times the sine of x. I'm trying to solve for a and b right now, okay? So what I really can say is that this cosine coefficient has to be